In this session, we're going to look at the four basic flip-flops: the set reset, the D, the toggle, and the JK, or the universal flip-flop. In the last video, we looked at a set reset flip-flop that sampled on a falling edge. Well, you can also find set reset flip-flops that sample on a rising edge, so we can see one here. So there's no bubble here, and in the truth table for the device, we can see a rising edge clock. So now, instead of on that falling edge, we're going to sample on the rising edge. So we're going to come down to our timing diagram and mark those in. Now we're going to go through at each of those points. So we have a set and a reset at this point, a set and reset are both low. So we're going to hold that value. So Q is going to stay low till that sample point. The next sample point, we have a set but no reset, so Q is going to go high, and it's going to stay high until the next sample point. At this sample point, set is low, reset is high, which means we're going to reset the device. It goes back low and stays low till the next sample point. Here, set is low, reset is high, so we get a reset again, stays low. Next one, sets high, resets low, so it's going to set, go high again, stay till the next sample point. And finally, set is low, reset is high, so Q is going to go low again. So you can see this time, the set pulse and reset pulse that we missed the last time when we were on a falling edge clock, we actually captured this time. The same way that the D latch compensated for the instability of a set reset latch, the D flip-flop that we have here will compensate for the instability in a set reset flip-flop. Here we can see the symbol for a D flip-flop. We can see the D input just like we had before, but now the enable has been replaced by a clock. Again, notice the little triangle indicating it's a clock pulse, so we're going to have some kind of a regular clock feeding into there. Outputs are the same. We have Q and Q naught, and we can see the truth table here. This case we have a rising edge device, so in there we're going to see up arrows. And on that clock edge, if our data is low, our output is going to follow. If our data is high, our output is going to follow that as well. Remember, our D device is like a transparent device. So here we have no bubble on our input, which means we're on a rising edge, so we're going to come and we're going to mark in the rising edges. Right away, you can see with these samples, we're going to miss some transitions on D. So again, clock speed is pretty important when you're choosing or setting up your system. Let's take a look at what happens to our waveforms here. Again, we're going to start Q off low, and we can take it low right to that first transition point. Here, we look and we say D is low, so that's the value we're going to store until the next sample point. Next sample point, D is high, so like a good D flip-flop, it follows the input and the output becomes high. Next sample point, D is still high, so this stays high. Next sample point, D is low, so our output follows and drops low. Last sample point, our input is low, so our output stays low. So even though this is a transparent device, we can see that we lost a lot of transitions on our data through here. On the output, it appeared as just high, so we lost a few of these low points in our information. Again, that's based on the clock speed. The faster the clock speed, the more often you sample, the more accurate your output is going to follow. The next flip-flop we're going to look at is the T flip-flop. Now the T stands for toggle. And it's a kind of a neat little device. You can see its symbol over here. Again, clock driven. Oh, we're missing the little triangle there. There should be one there, so let's put that in. Any flip-flop, you're going to see that triangle. Our input is T for toggle, And the way it works is, in this case, we have a falling edge clock, so we're going to see a down arrow here in our truth table. And the way it works is if it's activated, in other words, if T is 1, the output is going to toggle, and we mark that with another T. Toggle means it's going to change state, so if it was 0, it's going to go to 1. If it's 1, it's going to go to 0. Now, if the input is 0, it's like an on-off switch. So this is saying it's off. What it's going to do is it's going to hold whatever value it currently has. So let's take a look at our timing diagram. We have our clock pulse. Our schematic symbol tells us we're on a falling edge, so we're going to mark those falling edges in. That's where we're going to sample. So if it's high on the sample points, which it is here, not there, on the last one it is, so twice we're going to get a toggle. So let's see how that goes. We're going to start Q low, and at this first point we have a high on T, so that says toggle. Toggle means change to the opposite state, so Q is going to go high. Next sample point we have a 0, which says hold, so we're going to hold that high. Next sample point is a 0, which is a hold, so we're going to hold that high again. Next sample point is a toggle, so T is 1, so we're toggle. In this case we have a 1, so we're going to switch to the other state, which is a 0. So our output drops low at that point. So T doesn't mean it turns on, T means it changes state. The JK flip-flop is the last in the flip-flop family, and this one is considered the universal flip-flop. Just like we had universal gates, which are a NAND gate and a NOR gate, this one is a universal flip-flop, and that means that it can act as any of the other types of flip-flops. So we can see its symbol up here. So the inputs J and K, the clock, there's our little triangle. In this case, no bubbles, so that means it's a positive edge, or the rising edge. So the first thing we're going to come down is mark in those rising edges. Our truth table over here, we still have to complete. We have a rising edge here, so the first thing we're going to do is put those arrows in. And how does a JK flip-flop behave? Well, it's pretty much like our set-reset flip-flop. So if we get an active set, which is right here, so J is active, K is active, so think of J as S and K as R. So there's our active. We're going to get a set. When we have a reset condition, so that was reset active, set inactive, we're going to get a reset. So we're going to mark that in. When they're both inactive, right here, we're going to get a hold, just like we did before. And then this last one, which has been our problem right from the very beginning, when they both go active, in a JK flip-flop, that very conveniently acts as a toggle switch. So now we don't have any of that instability that we have anymore. So let's take a look at our timing diagram. We got a bit of a problem here because it appears that those two are changing at exactly the same time. So if you ever encounter a signal changing at the same time as a clock signal, think about the propagation delay. So we're going to have a little bit of a delay here. So if you see that happening, think of this as going up a little bit after that and treat it as the initial state that it's in. So in this case, we would consider J to be low at this point. So here we have J is low and K is low. So we're over here, we're in a hold. What I'm going to do is I'm going to mark an H right on my timing diagram. I'm going to go through all my sample points and mark in an H, an R, an S, or a T. Then I'm going to fill in Q. So if we go to our next one, here we have J is high and K is high. So J is high, K is high. I'm going to get a toggle. So I'm going to put a T right there. My next one, I have J is high, K is high again. So I have another toggle. My next one, I have J is high, or J is low, K is high, which is a reset. So I have a reset here. And then finally I have J is low, K is low, which is a hold. So now I can go in and I can fill in Q. So we start off low. The first one we have a hold, so we're going to come across to the next sample point where we get a toggle. We're going to toggle to high. Toggle means change state. Next one we get another toggle, so we're going to toggle back. Here we get a reset. Well, it's already low, so we stay. And we get a hold, so we stay low again. So the universality comes into play because we can see that in the first three states here, we have our set reset flip-flop. In this last row, we have our toggle flip-flop. So we've looked after two of the other three kinds of flip-flops. The last one is the D flip-flop. So how do we make this act like a D flip-flop? Well, remember the whole purpose of a D flip-flop was to ensure that set and reset were never the same thing at the same time. So what we can do is, on our inputs, much as we did converting a set reset latch to a D latch, we can add an inverter out front, and our input D comes in straight into J, through an inverter into K, and we now have handled our D flip-flop as well. So here we can see the full family of flip-flops. We have our set reset flip-flop, our D flip-flop, our T flip-flop, and our universal or JK flip-flop. So you can see the symbol is pretty much the same for all of them. We have the triangle in here indicating a clock input. That clock rising edge or falling edge is indicated on the timing or on the truth table, as well as the regular inputs. So our set reset flip-flop, if we get an active set, we set. If we get an active reset, our output clears or is reset. If we get both of them inactive, it holds, and if for some reason both set and reset go high, the device will become unstable. Our D flip-flop clears that up. We have a D input, which is our data. We have our clock input, both shown in the truth table. On that falling edge, if D is 0 when we sample, Q is going to reflect that and also be 0. If D is 1, it's going to window through and give us a 1 out. Our T flip-flop stands for toggle, so we have our T input. If it's high on the clock edge, then we're going to toggle to the alternate state. If it's low on that clock pulse, we are going to hold whatever value we currently have. Our universal flip-flop has a J and a K input that 3/4 of the time, in other words the first three rows in the truth table, acts like a set reset, but if it goes into that final state where both of them are active, it acts like a toggle flip-flop. Again, we can see with the bubble here, we're on a rise or a falling edge of the clock, giving us our Q output and its inverse.